This is EE300 Fall 2016, Module 3, Video 6, Op Amps, Operational Amplifiers. That's what we want to talk about today, is operational amplifiers. There's two main configurations we'll talk about, the non-inverting amplifier and the inverting amplifier. There's a special configuration of the non-inverting amplifier called the voltage follower. We'll summarize what we did and take a look ahead. So op amps, what are these things? These are 5-terminal devices. There's two inputs, the non-inverting input with a plus sign at the terminal, and the input's designated V+. The inverting input, the minus sign at the terminal, and the input's designated V-. There's associated currents I+ and I- that go with those. There's the supply terminals, VCC or VS, often designated. So VCC is the plus positive supply and minus VCC is the minus supply. The associated currents there I've labeled I1 and I2. There's no standard for labeling those. And then V out, VO, that's an O, cap O, not a zero. V out is the output terminal, and I out is the associated current there. So what are these things? They're electronics. There's about 20 transistors inside each one. It's a three or so stage circuit with some associated circuitry that goes with it. There's a differential amplifier at the front, and then there's a stage with voltage gain, and then there's a final stage that provides current gain. It's got high input resistance, so the currents I+ and I- are small. They're often opposites of each other. The thing is often modeled as having a resistance between the plus and minus terminal. It's a very high resistance, like in the mega ohm area. So I+ and I- are very small. It's got a low output resistance, so it can draw a lot of current without changing the voltage at the output. And it basically operates as a high gain differential amplifier. That is, the output is a scaled difference of the input at the non-inverting terminal and the inverting terminal. And how big is the scale factor? Big, 100,000 or so. So we'll see what that means here in a second, but you can imagine okay, the supply terminals here are usually like 15 volts, plus or minus 15 volts. So the output can't be bigger than the voltage supplies. I mean, that would be magic. So somewhere the output here is in the tens of volt range, or between plus and minus 15 volts. So if this gain is 100,000, then that means that the voltage difference between V+ and V- has to be in the microvolt, or the microvolt, the tens of microvolts kind of scale. Not very big at all, especially compared to inputs that could be on the size of, say, volts. So it's an interesting device we've got going here. So how does it work? Well, again, as we just said, that the output's going to be between plus and minus VCC. So it can't be bigger than supply voltages. This is where the power comes from, the VCC and the minus VCC. Nothing. These are just sensing, basically. You're just looking at what V+ and V- are. As we noted, it's got a high gain. And if it does have this high gain, if A is 10,000 or 100,000, and again, these are on the order of volts, then if V out is on the order of 10 volts, and these are on the order of volts, then if the difference between them is in the microvolt range, then these two are effectively equal to each other. Okay, and since they draw little current, since there's little current coming in here or going out, if it's negative, those currents are approximately zero, which means that all the current going out comes from the supply terminals. Okay, and that sort of makes sense. That's the whole idea here. We have a high impedance, high resistance input over here. We just look at V+ and V-. We decide what we're going to do. We make V0 big based on the difference between these two. And then however much current it takes to make that happen comes from the power supply. That's what the power supplies are. You're hooking this up to an external power supply. So that's where that power is coming from in the form of those currents, I1 and I2. So how do we analyze circuits using the op amp? We use what's called the ideal op amp assumptions. We pretend it's an ideal device, and in the idealization, there's no current that goes into the plus or minus terminals. So we say I+ is equal to I- equal to 0. And since there's very little difference, it's on the difference of microvolts here between V+ and V-, we treat those as being equal. Then we hook our device up. We use resistive circuit analysis like we always do. And then whatever we get for the output, we check to see that this V out is not bigger than VCC, or smaller, more negative than minus VCC. And when we start drawing circuits, we'll just leave the supply terminals off. It just clutters a diagram. So here we go. Here's a non-inverting amplifier circuit. You've got an input VS hooked up to the non-inverting terminal through a resistance RS. And then you've got the output connects to V minus through a resistance R1, a feedback resistor actually. And V minus is also connected to ground through a resistor R2. So let's see how this works. Since there's no current going in the plus terminal, V plus is the same as VS. And so, and since we assume these two, V minus and V plus, are the same thing, then the voltage of the inverting terminal is also Vs. But the output over here, since there's no current going into the not inverting terminal, R1 and R2 make a voltage divider for V0. So V minus is also the voltage across R2 by this voltage divider. So that means that Vs is equal to the voltage divider of V out, and we can solve that for V out, and we see we're going to get a gain. And the gain is going to be entirely determined, even though there's a huge gain in here of 100,000, the actual gain is going to be determined entirely by what we hook up to it. So we can it's a great little, that's why it's operational amplifier. That's the operational part of it. It just lets you do things with it in a very convenient way by what you hook up externally, regardless of the fact that it's got this huge gain and the voltage here is very small and all that kind of stuff. It's a great little box. It supplies enough current. So you see what happens. Okay, let's say we've got a V plus here. Say V plus gets bigger. V plus gets bigger, then that's going to make the difference between V plus and V minus bigger. That makes V out bigger. That makes the voltage divider voltage bigger until it gets to be the same. So, I mean, it's a feedback kind of system here. We see what are the constraints on when this will be true. When will V out equal R1 plus R2 over R2 times Vs? Well, that depends on the voltage divider relationship here being such that the voltage divider, magnitude of Vs has to be less than R2 over R1 plus R2 VCC. You just invert this relationship here to find out, to see what it has to be. Let's see how that looks. Here's a non-inverting circuit, same circuit, except let's give it some specifics. Let's say R1 is 2 k ohms, R2 is 1 k ohm, and VCC is 15 volts. So the output voltage is going to be 3 times whatever the input voltage is. See, we're trading off huge gain here for a small gain of 3, but we got out of it. We can do this externally just by hooking up resistors. There's no more circuit designed to that. We get amplifiers for the cheap. So that's going to be true as long as Vs is less than 5 volts in magnitude. Because once Vs gets bigger than 5 volts, then Vout's trying to be bigger than 15 volts, and it's not going to be bigger than 15 volts. It's going to saturate at 15 volts. Notice this sucker doesn't draw any current because the current going in the plus terminal is effectively 0, and that's what makes V plus equal to Vs. So it doesn't draw any current. It's basically got an infinite impedance going into here. Looking into the input of this circuit here, it draws no current. And the output's going to be very low impedance because it can supply the circuitry in here, the amplification circuitry supplies all the current. So it's really a nice device. Here's what it does. The blue line here is an input voltage. I've given it a 5 volt sinusoid. And then it's got a gain of 3, so the output is going to be a 15 volt sinusoid. That's pretty nice. If you try and give it a bigger sinusoid, 10 volts, you see that it's going to clip and it's going to saturate until the input gets below 5 volts, and then it's going to be proportional. The straight looking line here is actually a sine wave. It's just that we've cut off, because of the saturation, the curved parts of the sine wave, and it's you just see the part that's fairly well approximated by a straight line. So, I mean, the orange line there is actually the scaled version of the blue line, and then it would keep going up to 30 volts if it could, but it can't. It can only go to 15 volts because the op-amp saturates. The power supplies only provide plus or minus 15 volts. In practice, that might be 12 volts, it might be 10 volts, it might be 5 volts and 0, it may not be symmetric, so you have to look at the specifics of the op-amp you've got on your circuit board, but the conceptual idea is it's a symmetric supply. Here's an example where we've got a network function here, which is the voltage divider between R2 in series with C with R1 here, and now we're taking that voltage divider and amplifying that with R3 plus R4 over R4. So for these specific, you can see how we did the analysis over here. Here's the gain due to the op amp, R3 plus R4 times R4. Here's the voltage divider between R2 in series with C and R1. And now we do our usual arithmetic. I've skipped one step here just to save space on the page here, but you can see you get S plus 1 over R2C, 0 at minus 1 over R2C for the numerator here, and then in the denominator you've got S plus 1 over sum of R1 plus R2 times C. And we plug in these values here. We see that with the R3 and R2 both being 10 and R4 and R1 both being 90, these both sort of cancel out. So we get the voltage, the scale factor, the 10 gets killed off here, but we're left with S plus 10 times S plus 1. So we've got a 0 at minus 10 and a pole at minus 1. You can see that if we put a step in here, it would have a DC gain of 10 because S equals 0. So you can see that over here on this part, there would be no DC gain. So the gain is coming all from the amplification part of the circuit. So we may not have been able to implement this circuit without using op amps. And we'll see that when we come back to our design part. That this is a tool we use to implement circuits that require some gain at the low frequency stages. Okay, let's look at the inverting amplifier. This is a different configuration. Notice that the inverting terminal is shown on top here, the non-inverting on the bottom. The non-inverting is tied to ground, which is going to tie the V plus to 0, which makes V minus equal to 0. So the current that's going to come through here is going to be, now it's going to draw a current, which is going to be a Vs divided by Rs. So it's going to have an input impedance of Rs. And that current's not going to go into the amplifier because of the current going into the op amp being 0 there. So all that current goes through RF and basically determines what V out is. So, and as if it's 0 and this current is going, if the Vs is positive, current's going that way, which is going to make V0 negative. So here's the actual analysis. We sum the currents at the inverting terminal. So we get Vs over Rs plus V out over Rf equals 0. And so V out must be minus Rf over Rs Vs. This is a fairly common, famous formula, the inverting amplifier formula, minus Rf over Rs times Vs. Again, we can check and just invert that and take magnitudes to see how big Vs can be before it saturates. So here's an example where we've picked a 2 kilo ohm feedback resistor, a 1 kilo ohm source resistor. Again, VCC is 15 volts, not shown, but it's there. So at the, I don't know why I left, KCL at the inverting terminal doesn't matter. We use the formula V out equals minus Rf over Rs, and we get a gain of minus 2, which means that the input can go up to 7.5 volts before it saturates. And as we noted before, the current, this sucker's going to draw current compared to the other one. So the voltage drop is going to be Vs over there, and it's going to give us an input impedance of Rs. So here's the same 5 volt input, and now we get a 10 volt sinusoid except it's inverted. And if we turn up to our 10 volt input, we don't get as much clipping because, again, we don't get to 7.5 volts. We get to 7, more of the cycle is between plus and minus 7.5 volts than was between plus and minus 5 volts in the case of the non-inverting amp with a gain of 3. It's a little different when we do this with energy storage elements. So here's a circuit where we have an R1 in parallel with C1 as the source impedance and an R2 in parallel with C2 as the source, the feedback impedance. We can do that. Where we've got a resistor, you can put an impedance. So if we look at either of these circuits, they're going to have the parallel resistance of R parallel C, which is 1 over C times S plus 1 over RC. And now the network function from between V2 and V1 is going to be minus ZF over ZS, where ZF is the feedback impedance, C2 in parallel with R2, and ZS is the source impedance, C1 in parallel with R1. So we just replace this circuit here, the parallel formula, with R2C2 is appropriate or R1C1 is appropriate. Bring the S plus 1 over R1C1 up top, bring the C2s and C1s out, and we see that with these parameter choices of C1 equals C2 of 10 microfarads, R1 10 kilo ohms, R2 100 k ohms, we get the same network function, S plus 10 over S plus 1, but with a minus sign in front of it. And, would that matter? if you're doing something, a single stage circuit, and if this input goes up, the output has to go up because you're controlling something, you're expecting an input that's say between 0 and 10, and this is between 0 and 5, well, then you've got to do something to invert that again by making another inverting amplifier with a gain of -1 to get rid of the minus sign. If it's sinusoids and you don't care about the phase, then this is going to have the same frequency response, the same sinusoidal steady state responses as the previous circuit, and so it doesn't matter. So we get to the issue of design considerations and constraints external to the design that are going to determine which kind of circuit we use. Okay, let's look at the voltage follower, which is a special case of the non-inverting amplifier. Here you can see that the resistance to ground is infinite and the resistance to the output is 0, and that gives us a gain of 1. Basically, R2 is infinite here, R1 is 0, and so that just goes to a ratio of 1, so the output is just going to follow the input. What good is that? Well, we noted that there's no voltage gain in this circuit, but there's still current gain. There's no current drawn at the input because there's no current going into the non-inverting terminal, but now the output, the amplifier, can provide arbitrary or quasi-arbitrary current to deliver V out equal Vs. That makes this good as a buffer. Let's take an example of this. We've had these circuits before. Here's just a simple voltage divider between a capacitor and a resistor. These have the same network function, the same transfer function. They just have different inputs and outputs. What if we hooked them up together? What if we hook the second circuit with this V1 pair up to this the V1 pair of the first circuit? Can we multiply the network functions H1 of S and H2 of S? Well, we've worked this circuit in class before, and we know that we can't. The second voltage, the output voltage here, is a voltage divider between R2 and C2, but when we hook these up together, the voltage divider between R1 and C1 falls apart. Now we have the voltage divider between R1 and C1 in parallel with R2 in series with C2. So we have to work through the details of that, and we've done that previously, and we find that V2 of the network function for this circuit, when they're hooked up together, it's a second order circuit. But it's not the product of the original first order network functions. So the problem is that when we hook R2 C2 circuit up here, this R2 C2 network draws current from the R1 C1 network, which keeps the R1 C1 from acting like a voltage divider. Here's the same circuit though with the voltage follower inserted. So now, since the non-inverting terminal of the op-amp draws no current, the voltage divider between C1 and R1 holds. That voltage divider shows up at the output of the op-amp now because of the buffering properties of the voltage follower, and now we have R2 in parallel in series with C2 dividing the voltage V1, which is not impacted by the fact that we hooked the second network up to it. So we can actually say that V1 is the original H1, which is the voltage divider between C1 and R1. V2 is the voltage divider C2 R2 between V1, and now the network functions multiply. So V2 of S over V out of S is in fact H1 times H2. The voltage follower acts as a buffer between these two, so we can actually hook circuits up in cascade, and now when we hook them up in cascade like this, we can multiply their network functions. That's going to be a great and powerful thing that we can do. It makes our lives a lot easier. So what we've done is we've introduced the op-amp. It's a high gain, high input impedance, low output impedance device. The voltage output has to be between the supply voltages. So if we've got plus or minus 15 power supply connection to this thing, the output's going to be between plus and minus 15. It does. You give it a gain of 100 and put in 1 volt, it is not going to put out 100 volts. We've looked at both non-inverting and inverting configurations, and I didn't make a big deal about it, but all of these have the buffering aspect. The inverting may draw current from the circuit it's hooked up to, but the output of that thing can supply as much current as it needs to within constraints of the power supply. We saw the voltage follower, which was a special case of the non-inverting and is used explicitly as a buffer. So where do we go from here with these? We're going to be able to design arbitrary low order, first, second, third order circuits, because now we can design with real poles and even with complex poles, we'll see, because now we can hook up first order circuits to another first order circuit to another first order circuit. And so we can certainly cascade first order circuits to generate sets of real poles on the negative real axis. So design is what's next. We've got the tools we need with our what we've done previously and now with op amps. So this has been EE300 Fall 2016, Module 3, Video 6, Operational Amplifiers.